Alrighty, let's get started for today. So in this video, we're going to continue our discussion of linear algebra. Last time we talked about vectors and the new vector notation we have. We have some vector v, and it is a column of elements where, let's say, maybe we're doing three-dimensional vectors, some kind of physics, and we're talking about the position of an object in 3 dimensions. Then this is going to have some x component in the first slot, some y component in the second slot, and some z component in the third slot. Okay. Now, generally speaking, especially when we're talking about mathematics instead of just physics, these vectors don't have to relate to things like the x direction, the y direction, and the z direction. They can be in some abstract vector space where the different directions might mean position and momentum, for instance. It's kind of weird to think of it that way, but you can do this. It's just that for us, especially if we're engineers or physicists, we like to relate these mathematical ideas to something physical. And so the most easily imagined version of a vector is just as we see normally in class. We have some 3D space. Maybe this is x, this is y, and z is coming out towards you. And you have some arrow pointing out. Maybe it points out a certain distance kind of out of the screen, up and to the right a little bit. And this arrow relates to something. Maybe it's the position of an object, or maybe it's the speed at which an object is moving. Whatever this vector is, it has a magnitude, which is the length of the arrow, and a direction, which is in which direction does this arrow point. And so obviously, it's nice to go ahead and think of it as being in a 3-dimensional space, or 2-dimensional space if we have a 2-dimensional vector. And so each of the elements of our vector relates to an x component, a y component, or a z component, something like that. And we saw in the last video how we can do some algebra with these things called vectors. We can add vectors together, we can multiply vectors, and in fact when we did multiplication, we saw that there's 2 different versions of multiplication. There's dot products and cross products and things like this. And we also saw we can find the length of our vector, or the magnitude of our vector, and that's basically the Pythagorean theorem. We saw that the length of a vector, you could call it like this, is the square root of the x component squared plus the y component squared plus the z component squared. Right? Basically, in linear algebra notation, it's v dotted with v, and then you take the square root. Okay, so v dotted with v means x, y, z dotted with x, y, z. And we saw that to do a dot product, you take the x component, or the first element, times the first element, so x squared, and then you add to it the second element times the second element, y squared, and the third element times the third element, which is z squared. And then if we want the magnitude, not the magnitude squared, we would then take the square root of this thing. And that's the Pythagorean theorem. This version of it is the 3-dimensional version, the one you usually see with right triangles, where this is A, this is B, and this is C. The length of the hypotenuse, C, is the square root of A squared plus B squared. The x piece squared plus the y piece squared. In 3 dimensions, you just add in the z dimension. And of course, you could have this in higher dimensions, 4-dimensional space, 5-dimensional space. You just continue to add on the other elements squared, just like that. So it generalizes. Today's video, what we're going to talk about are matrices. This is the plural. Of course, matrix is the singular. A matrix is another object in this linear algebra space. Just as vectors are an object, they're the things that we're working with usually. Well, a matrix is something new, some new object we could put into this topic. And basically what it's composed of, one way to think about it, is you could think about, let's say we have a vector v and a vector u. Maybe vector v is AB and vector u is CD. Well, I can kind of combine these two vectors together into a single object and then use that single object to do some operations and so forth forward. Maybe I could do some operations on other vectors. Maybe I could do operations on other matrices. Why we're doing it, don't worry about that yet. This is just, we're kind of playing around with the rules. What's allowed by this version of math? And then hopefully, once that's all been set into stone, what we're allowed to do, what we're not allowed to do, then we will try to find what's useful about it. Why would we want to do this stuff? And it turns out that in physics and in other areas, there are a lot of uses for using matrices. For instance, if we want to take, let's say, a vector like this vector here, vector v, and maybe we want to rotate it so now it's pointing in another direction. Well, what do you do to the elements of this vector in order to make this vector now point in some other direction? We don't want to change its length. We want the magnitude to stay the same. For instance, you're walking 20 meters, or you're running 20 meters per second to the right, and someone says, I need you to run 20 meters per second upward to the north. Well, you have to continue running at 20, but now what you want is your direction to change. And so how do we modify a vector to keep its magnitude the same, but now have its direction changed into some new direction that we're interested in? Well, one of the things we could do with a matrix is exactly that. That's called the rotation matrix. It takes a vector and rotates the arrow to point in some new direction that we want it to point in. But there's a whole lot more to it than just that. That's just a single example. So anyway, getting back to kind of the general rules of things, we're going to create this new object. And the way it looks, let's call it the matrix M. Sometimes you'll see a bar. Sometimes you'll see a bar on the bottom. I'm not worried about that. Just like I don't usually draw the vector arrows. Formally, that formatting is true, and you have to worry about it if you're doing scientific papers and things. But for the class, let's not concern ourselves too much. We have the matrix M, and it's going to look kind of like a column vector, except it's going to have multiple columns. So it's got the parentheses, and we'll have the first column, AB, and then we'll have another column next to it, CD. And now we have some new object. This is called the matrix M, whose elements are A, C, B, and D. Now, the order you write these, or the order that you discuss the elements, like if someone says, what are the elements of the matrix? Do you say A, B, C, D, which is going from left, you go top to bottom, then you go to the next column, top to bottom, and so forth? Or do you say A, C, B, D? Which is like you're reading a book, left to right and then top to bottom. Usually, especially here in the United States, we go left to right, top to bottom. So you would say the elements of this matrix M are A, C, B, and D. But that's just kind of, a standard that we use. There's no reason you couldn't do it the other way. Another thing that's important about the notation and things like this is if we want to talk about a particular element, so let's say I want to tell you, take the C, whatever number this C is, and take that number and we're going to use it to do something. So maybe, I want you to take this element C and multiply that times the vector V. I don't know why I'd want to do it, but let's say that's what I want to do. How do I tell you which of these elements in the matrix I need you to take out and use to do an operation. Well, the formatting here, the symbology that we use, is we say the matrix M, first of all, the size of the matrix, because you could have matrices like this, A, C, E, B, D, F. You could have a matrix that looks like that. That's kind of ugly because it's not square. It's not the same number of rows as columns. You could have A, B, C, D, E, F, G, H, I. Now you have a square matrix. Square meaning the number of rows. So row 1, row 2, row 3 is equal to the number of columns. Column A, column B, column C. This matrix is not a square matrix because there's more columns than there are rows. But if we wanted to say, this matrix M I'm working with has this many columns and this many rows, or actually this many rows and this many columns, you would say it's M, N by M, let's say. N by M matrix. Now, I guess what I should do, just to avoid confusion, is, let's call this the matrix, I don't know, give it some other name, T. So that M means a number. Like there's 2 rows and 2 columns, things like this. So, let me just go ahead and do this. Let's say you have the matrix T, it's M by N, which means the number of rows is M, and the number of columns is N. So, for our matrix M here, M is a matrix which is 2 by 2. 2 rows, 2 columns. This matrix, this M, would be 3 by 3. This one, if this was M, this would be 2 by 3, and so on. So a matrix has the size, number of rows, number of columns. 2 by 2, 2 by 3, 18 by 45, whatever it happens to be. And in fact, you could have infinitely large matrices. When we deal with quantum mechanics, the matrices that are there, a lot of them, depending on what things we're trying to work out, have to be infinitely long. So, infinite by infinite matrices. That's fine. Now, getting back to the point of what I was talking about, if I want to pick out, let me go to a clean sheet. Let's say we have our matrix M, and we'll have it A, B, C, D. If I want to pick out a particular element, I need some notation to say, get this particular element from the matrix. And the way it goes is like this. We'll say, take the element 1, 1, that's A. So this element here is the first row, first column. The matrix element 2, 1 is the element B. It's the second row, first column. 1, 2, that's C. And of course, 2, 2 is D. So if you're given some matrix of some number of elements, whatever it is, it could be a square matrix, it could be a non-square matrix, whatever, and someone tells you, I need this particular number, whichever number it is. Well, how do you know which element that is in your matrix? It's the row, then the column. So 2, 1 means go to the second row. So first row, second row. And then look at the first column. This is the first column, and that's the element B. Okay. Now what else? What else do we want to know about matrices? Well, as is usually the case, once we know what a matrix is and we have our ability to write it down and we have our symbology and all that kind of stuff, now we want to start doing some operations. And a basic operation we can think of course, is adding. Can we add two matrices? Well, first of all, there's a rule about adding matrices, just like there's a rule about adding vectors. When we saw vectors, if we want vector v plus vector u, we were told we're only allowed to add these vectors if they happen to point in the same direction. If they don't point into the same direction, you just can't add them normally. However, we did find ways of getting around it by saying, well, if we want to add two vectors together, what we can do is we can add the x pieces with the x pieces and the y pieces with the y pieces. So we add them element by element, is called. So maybe we have A, B, and we're trying to add to that C, D. Of course, with this kind of a notation, it's very easy, unlike when we did general physics, and we have vector v is 10 meters at an angle of 30 degrees, and vector u is 20 meters at an angle of 120 degrees. There we had to do x and y components first, add the x's with x's, y with y's, and then square root magnitude and direction. Here, with this notation, it's very easy. We get some new vector where we add the x element with the x element, so a plus c, and then the y element with the y element, b plus d. Okay? Well, the same is going to hold true about matrices, only for matrices, the limit or the limitation we have, just like the limitation for vectors is their direction has to be the same normally, and we get around it by doing this element to element thing. If we have two matrices, M plus N, if these two matrices are not the same size, then you can't add them together. Okay? You can only add together matrices of the same size. So if this is a 2 by 2, and this is a 2 by 2, then we can add them. And how do you add them? Well, let's take two matrices. Let's say A, B, C, D. There's that one. And then maybe this is E, F, G, H. And I want to add these two matrices together. Well, it's fairly obvious once you see how we did vectors, we're going to do the same kind of a thing for matrices. If you want to add these two matrices together, if they're the same size, then you add them element by element. So we're going to get some new matrix. The first element is the first element here plus the first element here, A plus E. Okay, so that's some number. All right, the next one, C plus G. So over here is C plus G. Then B plus F, and of course D plus H. Okay, so I have a 2 by 2 matrix plus a 2 by 2 matrix. I get a 2 by 2 matrix. The elements of this 2 by 2 matrix are just the sum of each element of the original matrices. So the first element of my answer is the first element of M plus the first element of N. Likewise for second, third, and fourth, and so on. Okay? And then, of course, if we're subtracting two matrices, all you have are negatives instead of positives there, if this is a minus, for instance. Okay, so adding matrices, very easy once you have this notation down, because everything's already in x and y components and things like that. So you want to add these two matrices. First of all, you better hope, you better make sure that the two matrices are of the same size. So for instance, if I have A, B, C, D, and I want to add to it 1, 2, this is, you can call it a matrix, even though we've been calling these things vectors, but it's just a matrix which is only a 1 by 2. I mean a 2 by 1, I'm sorry. 2 rows, 1 column. Well, if I wanted to add these, I can't. How do I add them? You know, I could, okay, first element with first element, so A plus 1, that's fine. But then this element plus this element, that's okay, B plus 2. But then what about these? How do I get those two elements? What do I do with these C's and D's? There's nothing here. They're not 0. It's not 1, 0, 2, 0. That would be some other matrix. These two things are not the same. This is a 2 by 2 matrix. This is a 2 by 1 matrix. So you want to add two matrices together, make sure they're the same size. Now, if they are the same size, great, very easy to add. Just add element by element. First element plus first element gives you the first element of your answer. Second element plus second element gives you the second element of your answer, and so forth. Okay, so let's do a little example of what I've been talking about. Let's say we have the matrix M is 1, 0, 2, 3, and N is 3, -1, 4, and 2. Okay, and my question is, if M plus N gives you some new matrix T, give me T 1, 2. Okay? So what this is saying is, I'm giving you two matrices, M and N. They're both 2 by 2 matrices, so that's good. I'm claiming that if you add the matrix M plus the matrix N, you're going to get some new matrix T. And what I want you to tell me is, what is the answer? What's the number? What's the element 1, 2 from that new matrix T you just got? Okay? So that's what I want. Just a single number. I don't want an answer as a matrix. I just want this element only. Okay, well, let's find out. Let's first add the two matrices together. So I have 1, 0, 2, 3. And I'm going to add to it 3 minus 1, 4, and 2. What do I get? Well, first of all, these are both 2 by 2 matrices. They're the same size, so I can add them. Good. To add them, I take 1 plus 3. That gives me 4. The next element, 0 plus -1. That gives me -1. Next element, 2 plus 4. That gives me 6. And finally, 3 plus 2 gives me 5. So that's my new matrix T. Now that I have this matrix, all I need to do is find what is this element. Well, that element is the first row, second column. So first row is this row right here. Second column is this column right here. So all I want is that number. So T 1, 2 is -1. There we go. Okay. Very straightforward once you get used to the notation, and you have to be careful because it's easy to kind of forget. Is it row then column or column then row? It's row then column. So T, M, N. M is the row, N is the column. Okay. Now, next time what we're going to do is we're going to talk about multiplication. How do we multiply matrices together? So say we have A, B, C, D, and I want to multiply it by the matrix E, F, G, H. The question is, how in the world are we going to do this? We saw that with vectors, there's multiple ways of multiplying. The easiest one, of course, is the dot product, and that says AB dotted with CD. It said, well, take the first element times the first element, AC, add second element times second element, BD. And of course, if these were longer vectors, then we just keep adding more and more. But is this true for multiplication of matrices? Matrix is something different than a vector. If I want to multiply these two matrices, is it just this simple? Well, it turns out no. Of course, it also depends on what kind of multiplication we're talking about. But for the multiplication we're generally going to be using, when you multiply two matrices together, it's a little bit more complicated than this. And in fact, the answer we get is not a number like with vectors and a dot product. It's more like how we do cross products with vectors, where we have this vector crossed with this vector gives me a new vector answer. From multiplication of matrices, that's what we're going to do. We're going to multiply these matrices in a certain way, whatever this way is, and the answer we get is going to be a new matrix. So that's what we're going to do next time. For now, get used to the notation about matrices, get used to how to add matrices together, things like this. But it's fairly straightforward once you get used to it. And next time, we'll complicate matters with multiplication. Anyway, hope this is helpful, and I'll see you next time.